last time in section 7.2, then we talked about categorical variables and looking at categorical variables with multiple levels. So we were comparing essentially multiple proportions. And here in chapter 8, what we're going to be looking at is comparing multiple means. So last time we were dealing with categorical response variable, and in chapter 8, we're dealing with a quantitative response variable, which is why we're comparing multiple means, 3 or more means. And our basic strategy is going to be the same as it was in chapter 7. So how we're going to deal with comparing 3 or more means. First of all, we're going to do an overall test to see if there's any differences among the means. And then second, if that overall test is significant, then we're going to do a detailed follow-up analysis. So the overall test that we're looking at is called analysis of variance. And we often abbreviate by just calling it ANOVA. So the AN from analysis, O from of, and VA from variance is where that ANOVA comes from. And the basic idea behind analysis of variance is we're going to be comparing variation among the sample means to the variation among individuals in the same sample. So we want to know how different are the means versus how much variation are we seeing just within individuals in the same sample. So our hypotheses for this overall analysis of variance test, the null hypothesis is going to be that all the means are equal. So depending on how many groups we're comparing, that'll tell us how many means we're looking at here, but we're going to have null hypothesis mu1 equals mu2 equals mu3 equals mu4 equals mu5, et cetera, for however many groups are being compared. And then the alternative hypothesis is a little bit different than what we've been seeing. The alternative hypothesis is going to be that at least one mean is different from at least one other mean, okay? Or you can really just say at least one mean is different. It's a little easier to say. All right, so we can say that at least one mean is different for the alternative. So this is important to note that the alternative is not that all the means are not equal, okay? So we're not requiring that all the means are different from each other. We're just saying that at least one of the means is different from at least one of the other means. So if we think about the test statistic for this overall test, when we've talked about test statistics before, we've followed this kind of basic pattern of a sample statistic minus a null value divided by a standard error. But in the case of comparing like 5 means or something, then this isn't really going to work because we have lots of sample statistics and we have lots of null values. So we can't just plug things into this nice, neat formula like we have in the past. We're going to need something a little bit more complicated. So whether or not 2 means are different depends on a couple of things. So it depends on how far apart the means are and how much variability there is within each group. So it depends on those 2 things. So our test statistic is going to compare those 2 things. So it's going to compare how far apart the means are to how much variability there is within each group. So the test statistic that we're going to use is called an F-statistic, and I'm not going to give you a formula for computing the F-statistic in our class because it's a little bit more complex than what we want to get to in our class here. But if you're dying of curiosity, then you can go read all about it in the textbook because it does explain how to do that there in chapter 8. So this isn't the formula per se for the F-statistic. This just explains what the F-statistic is doing. Okay, so the numerator of our F-statistic is going to be a variation among the sample means. So it's saying how different are the means of the different groups that we're comparing. And then the denominator just says, okay, how much variation are we seeing among individuals in the same sample? And if you want, you can write this part down here, but you don't need to. This is kind of a nod to the calculations that we're doing to get these numbers, but I'm not going to require you to know this part. So just this other part is good to write down. Unless you already wrote the other part, it's fine to write that part down. but this helps you get a general idea of what this F-statistic is doing. So I mentioned that we're not actually going to compute by hand the F-statistic in our class. We're going to have StatKey compute it for us, or we're going to identify it on some output from another statistical software program. So the main thing you need to know is that the test statistic for ANOVA is an F-test statistic, and you need to be able to find that test statistic in output. Oh, here's the explanation. So the F-statistic is a ratio of the average variability between the groups to the average variability within the groups. So basically, if you kind of think about what this test statistic, this F-statistic is doing, okay, it's looking at, okay, how far apart are the means or the centers? I know in a box plot, these are really the medians, but since these are all pretty symmetric distributions, the mean and the median should be similar. So if you look at these box plots, we're trying to say, okay, how far apart are the centers here, the means, versus how much variation are we seeing within a single sample? And visually, you can see this on a box plot pretty well. So if I'm comparing, say, A and B, okay, which one do you think has better evidence of a difference between group 1 and group 2? Does the box plots in A show more evidence, or the box plots in B? And if we have more evidence, then that means that it's going to have a smaller p-value, right? Because smaller p-value equals greater evidence against the null, so in favor of a difference. Right, B. Okay, B, you can see that the means are further apart compared to how much variation that we're seeing within the group here. All right, what if I'm comparing A and C? Which one of these would have bigger evidence of a difference? So in other words, a smaller p-value. Right, so C is definitely going to be bigger, and this one even looks farther apart. And you can look down at the numbers below too. They're kind of interesting because we can see that on A and C, we have like if we just compute the difference in the means, it's the same. Group 1 had 5, Group 2 had 6 for both groups. But if we look at the variation within a group, we can see that it's a lot greater for A than it is for C. So remember, the difference in the means is what goes in the numerator. So the farther apart that is, that's going to make our number bigger. And then the variation within a sample is that value kind of goes in our denominator. So the smaller that is, that will make our overall F statistic bigger. And a big F statistic means lots of evidence, which means small p-value to reject and things like that. Okay, this next one's a little bit trickier because it's not going to have graphs. It's just going to have our data there. Okay, so looking at these two groups and thinking about the same concepts here, which one of these groups, A or B, or which one of these tests would have a smaller p-value? So comparing the two groups in A or comparing the two groups in B. All right, so this one can be really tricky. Remember that our F statistic, we're comparing the means for our numerator, and we're comparing the variation in a sample. So in the denominator, roughly, okay? So if I look at the means here for A, I'm comparing 5 to 8. For B, I'm also comparing 5 to 8. So those are going to end up having like the same numerators essentially. But if I look at the variation in a sample, which one of these, A or B, has a smaller variation inside the sample, less variation among the individuals in the sample? A, right? A has less variation. So here, in this case, if I'm looking at this F statistic, we're going to have the same number on the top for both of them because they had the same difference in means. But there was a smaller variation in A, so I'm going to put small there, and there was a bigger variation in B. So if I look at this overall number here, which one is going to have a bigger F statistic? And a bigger F statistic means a smaller p-value. So A, right? So A is the one that is going to end up with the most evidence of a difference there because it's going to have bigger F statistics, smaller p-value. It's a lot trickier when you're looking at the numbers instead of the box plots. All right, so basically anytime we do an analysis of variance, then our results are going to be displayed in an ANOVA table. And this is the basic format of an analysis of variance table minus the p-value. Often the p-value is in another little box right over here to the side, which we'll see in just a minute. And a lot of these numbers you're not going to really care anything about because you're not going to have to compute any F-statistic by hand or anything like that. But if you're given computer output, you're going to need to be able to look at that analysis of variance table, be able to identify the test statistic. There's a few other numbers that we're going to end up identifying by the end of class as well. So knowing what an analysis of variance table looks like, what numbers you want to look at, and what numbers you don't really care about is going to be important. Okay, and for now, the most important thing is going to be the F statistic and possibly the p-value if they give it to you. So let's talk about the conditions for doing analysis of variance. And there's two conditions that have to be met. The first condition is that either all the samples are large, so greater than or equal to 30, or all the samples are normally distributed. So this is condition number one, and it can be met either of these two ways. So if the samples are large, we meet the condition, or if the samples are normally distributed, the individuals in the sample are normally distributed, we can meet that condition. The second condition is that all populations have the same standard deviation. And obviously we don't know the population standard deviations, but we can look at our sample standard deviations, and if they're pretty close, then we're going to say, okay, I guess, we meet this condition. And by pretty close, we have this little rule of thumb that we follow where we look at our sample standard deviations, and if the largest sample standard deviation is no more than twice the smallest sample standard deviation, then we're going to say that we meet this condition. So what I like to do is I just write out this inequality. I fill in the values of the largest and the smallest sample standard deviations. And then if it's a true statement after I plug in the numbers, then I meet the conditions. And if it's not a true statement, then I don't meet the conditions. And we'll see how to do this in an example here. So this F statistic follows a F distribution. So now we're kind of adding one more theoretical distribution to our toolbox. So we've talked about normal theoretical distributions. We've talked about T theoretical distributions. We've talked about chi-square theoretical distributions. And now we're talking about F theoretical distributions. And one characteristic of the F distribution is that it is right skewed. So who remembers of the other three theoretical distributions that we've talked about so far? What's the other one that is right skewed? Yeah, good. The one we talked about last time, right? The chi-square distribution. So the chi-square was a right skewed distribution. The F distribution is also right skewed. And for a similar reason, because remember when we're finding our F statistic, we basically have a variation number over another variation number. Okay, variation, same thing as like spread. And when we measure spread or variation, then we're talking about things like standard deviation, things like that. And it's impossible to have negative spread. You can't have negative spread. Okay, it always has to be a positive number. So because we're going to have a positive number over a positive number, then F can only be positive. So it's going to be bounded by 0, and that's going to make it into a right skewed distribution. Something that's different about the F distribution versus the chi-square distribution is that the F distribution has two types of degrees of freedom that are associated with it. So it's going to have a numerator degrees of freedom and denominator degrees of freedom. And depending on where you're looking, sometimes these numerator and denominator degrees of freedom end up with different names. So most of the time I'm going to refer to them as numerator and denominator, and that's what the NDF and DDF stand for here. But we're going to see later today that in StatKey, there's another place where we're going to look for the numerator degrees of freedom under groups. It'll be like the groups degrees of freedom, and the denominator degrees of freedom under error. And also another name, a third name, is that sometimes this is called the between groups degrees of freedom. So the numerator is sometimes called the between, and the denominator is sometimes called the within. If you see it asked for slightly different ways, just realize it's all going back to this same number. So numerator degrees of freedom is the same thing as the groups degrees of freedom, which is the same thing as the between groups degrees of freedom. Denominator degrees of freedom is the same thing as the error degrees of freedom, which is the same as the within group degrees of freedom. Okay, so let's look at how to calculate these degrees of freedom. For the numerator degrees of freedom, it's going to be k minus 1. And k is the number of groups that are being compared. So however many groups you're comparing, that number minus 1 is the numerator degrees of freedom. And our denominator degrees of freedom is going to be equal to n minus k. Okay, and n is the total sample size in all the groups combined. So if you add up the number of observations in all the groups, then that's what n is. And I mentioned that we will not be calculating the value of the F-statistic by hand. We'll always either be given that, or it'll be on some output, or you can use StatKey to find it. However, I will ask you to compute the degrees of freedom for the F distribution, because these are pretty basic calculations. All right, so we're going to look at an example here. And this example is about cuckoo birds, and I don't know how much you know about cuckoo birds, but basically what happens with cuckoo birds is that the mommy cuckoo bird, she gets all knocked up and she's like, hey, I don't want to change my lifestyle. I don't want to have to worry about a baby. So I'm going to ditch this egg somewhere. So the mommy cuckoo bird, she goes and she finds a nest that's just sitting there. No one's around. She hurries, she puts her egg in the nest, and she runs away so that she doesn't have to take care of her offspring. Well, then this little cuckoo bird egg, it hatches out of its little egg, and it looks around and it realizes that his mom is gone and that he's in a stranger's nest. And this little cuckoo bird is a little bit worried that he's going to be rejected. So what the little baby cuckoo bird does is he knocks all the other eggs out of the nest, gets rid of all of them, so that when the mommy bird of that nest comes back, she'll be like, oh my gosh, I'm so sad, all my babies are dead. But then she'll see this little cuckoo bird there and she'll be like, oh, at least I still have you. I will raise you as my own. Okay, so basically that's what happens. So we have the cuckoo birds, they lay their eggs in the nest of other birds. When the cuckoo baby hatches, it kicks out all the original babies, and then if the baby cuckoo bird is lucky, then the mother of that nest will raise the cuckoo bird as if it were her own. So what researchers wanted to know is, are these mommy cuckoo birds, are they being strategic when they're ditching their eggs in these different nests? Like, are they actually like looking around saying, hey, I have a little egg this time, I should find a little nest to go drop this in, or I have a big egg this time, I should find a big nest to drop this egg in, so that it blends in more with the other eggs in the nest? Or is the mommy cuckoo bird just like, get this egg away from me, first nest available, I'm just going to dump it and run? So what these researchers did is they went and found a bunch of cuckoo bird eggs in these different other species of birds' nests, and they measured the size, and they wanted to see if there was a different size, if the sizes differed depending on the species of nest that it was found in. Hopefully that made sense. So they had 5 different species of nests that they found these cuckoo bird eggs in, and here is a box plot of their results. Okay, so they measured the length of the cuckoo eggs that were found in these different species of birds' nests. So just looking at this box plot, does it look like there is a difference? Does it look like at least one species had a different size egg in their nest? Yeah, I think it looks like there's a difference too. Okay, so and specifically to me, it looks like the wren got a lot smaller cuckoo eggs in it than any of the other species here. So looking at this graph, it seems like there's probably at least one mean that's going to be different, but we're going to do this analysis of variance to see if this difference is statistically significant. Because remember, this is all based on sample data, so we want to know, hey, could we have seen these results due to chance, or is it pretty unlikely that we would see a difference this big with the wrens just completely due to chance? All right, so to do that, we're going to do this analysis of variance, starting with our hypotheses. So remember, the null hypothesis is that all the means are equal, and then the alternative hypothesis is that at least one mean is different. And in this case, we have 5 different groups that we're comparing. So we have 5 means that we're comparing. So my null hypothesis, my null hypothesis is going to be that mu1 equals mu2 equals mu3 equals mu4 equals mu5. All right, and if I was defining all my parameters here, it's a lot of parameters to define. Mu1 would be the mean cuckoo bird egg length found in, and let's see, what was my first group here? In a pied wagtail nest. Okay, so mu1, mean cuckoo bird length found in pied wagtail. I'm not really a bird enthusiast, so I don't really know the difference between these birds, but maybe some of you do. Okay, and then similarly, mu2 would be the mean cuckoo bird egg length for eggs found in pipit nests. Okay, and mu3 would be the mean cuckoo bird egg length for eggs found in robin's nest, okay, etc. Okay, so you get the idea for all those parameters. So the null hypothesis, they're all equal. The alternative hypothesis is that at least one mean is different. And you could even get a little bit more specific here and say something like at least one species had a different mean cuckoo bird length than at least one other species. All right, so now we have our hypotheses. We're ready to start looking at the data here. And to help us, we're going to just break down the notation here. So we are now dealing with 5 different samples. That means we have 5 parameters. We have 5 sample sizes. We have 5 sample means. We have 5 sample standard deviations. So there's a lot to keep track of. So here's the notation that we're going to use. Whoops. Okay, so we already talked about K. K is the number of groups that are being compared. And when we use N with a subscript, that's going to represent the sample size for that particular group. So N1 would be the sample size for the pied wagtail, for example. If we talk about N with no subscript, then that's going to be the total sample size for all the groups combined. So if I add, in this case, N1 plus N2 plus N3 plus N4 plus N5. If I add all those numbers together, that's going to be my N, my overall sample size. And we're going to use similar notation for X bar and S and the other values. Okay, so X bar with a subscript means that it's the sample mean for a particular group. So X bar 1 would be the sample mean for the pied wagtail. And then X bar with no subscript is the mean of all the data combined together. So here's a table that lists off the mean, standard deviation, sample sizes for all of our different groups. So there's 5 groups like we talked about. Okay, 15 is N1, N2 is 60, N3 is 16, N4 is 14. The overall number of observations, N, is 120. We got that by adding all these numbers together. For sample means, same thing. You know, we're going to have X bar 1 through X bar 5. If I take all the observations and find the mean of all the observations together, that's where this overall X bar comes from. And then same idea with our standard deviations as well. So we have S1 through S5, and then if we look at the standard deviation of all 120 observations, that's where the S with no subscript comes in. Okay, so next let's check our conditions. So the conditions are that all the samples are large or all the samples are normally distributed. So looking back here at my chart and my sample sizes, I can see that 15 is not large, so that one's a little iffy. 60, that one's large, so we're good on the pipit. Robin, not large. Sparrow, not large. Wren, not large. So for the pied wagtail, the robin, the sparrow, and the wren, I would need my sample data to be normal because the sample size is not large. And I can look back at the only graph I have of this, because this data came from your textbook, is this box plot here. And remember, the pipit is the one that had n equals 60. So we feel good about that one. If I look at the pied wagtail, it looks pretty symmetric with no extreme outliers. So that one's probably good. Same thing with the robin. That one looks pretty good. Sparrow has an outlier here. So I would say the sparrow is iffy. I'm not sure that we meet the conditions there. But the wren also looks pretty decent over here. There's no extreme outliers anyway. So we kind of meet that condition with the exception of the sparrow on that one. So I'm not convinced we meet the conditions here. Let's look at our second condition, which is the variation. So let's see, on this one, checking the conditions, we can say all meet except the sparrows. I'm going to say the sparrow looks iffy. So I wouldn't really say that overall we meet that one. For this second condition, that the populations have the same standard deviation, we're going to use our rule of thumb. Okay, so we want the largest S to be no more than twice the smallest S. So looking here, so again, I'll just write that down here. So largest S less than 2 times the smallest S. Okay, so looking at my chart here, what's the largest sample standard deviation? What's the value of the largest sample standard deviation? Yeah, 1.07. So 1.07 less than, and then which one is the smallest? So the smallest is going to be that 0.68. So if I do this computation here, I end up with 1.07 less than 0.68 times 2, which is 1.36. Okay, so is this a true statement? Is 1.07 less than 1.36? Is that true or false? Yes, it's true, right? True. So because this is a true statement, then that means that we do meet the condition for the variance that we talked about. So, so all populations having the same standard deviation, we do meet that condition. Just a note, when you're doing your homework or on an exam or something, if I ask you about this one, if they meet the conditions, I want more than just a yes or no. I want to actually see this computation worked out in order to know whether they meet it. So don't just look at it and be like, yes or no. You need to actually plug in the numbers, show me the calculation so I know you know what you're talking about. Okay, so overall, we met the variability requirement, but the sample sizes were small and we weren't sure about the sparrow being normal, so we're a little iffy on whether we meet the conditions overall. But we'll go ahead and do the analysis of variance anyway, so you can see what it looks like. So next thing we're going to look at is the numerator and denominator degrees of freedom. So remember, I'm not going to ask you to compute the F-statistic by hand, but I will ask you to compute the degrees of freedom. So for our degrees of freedom, the numerator degrees of freedom were equal to K minus 1. Okay, K is the number of groups that we're comparing. So how many groups are we comparing in this case? 5, exactly. So my numerator degrees of freedom will be 5 minus 1, which is 4. So I have 4 numerator degrees of freedom. And for my denominator degrees of freedom, that was equal to n minus k. N is the total number of observations. So that's this 120 number down here. So I'm going to have 120 minus 5. So k is the number of groups we're comparing. So I end up with 115. So one thing that I will tell you to just be cautious with when you're computing these degrees of freedom is these are pretty basic calculations. So you can, most people don't have a hard time with them. But one common mistake that I see frequently is because you usually do the numerator first and then you do the denominator, some people want to take this number here and plug it in down here. So instead of taking 120 minus 5, some people have that 4 number fresh in their mind, so they plug in the 4, which would obviously give you the wrong number. So just be careful as you're computing these and make sure that you're plugging in the correct numbers, and then you should be all good. All right, so I have my numerator and denominator degrees of freedom here. So I'm ready to look at my test statistic. Okay, so my test statistic I would find in the analysis of variance table in StatKey or on the computer output that's provided. And my test statistic in this case is F equals 10.19. So if it asks you for the test statistic, all you have to do is find it and say F equals 10.19. All right, and the next step is going to be to use that test statistic to help us find the p-value. So we're going to find the p-value inside of StatKey. Inside of StatKey, I'm going to be looking for the theoretical F distribution to help me find my p-value. So that's the last one over here. When you click on the theoretical F distribution, it's going to ask you for your degrees of freedom. So it asks for the numerator and denominator degrees of freedom. So I'm going to put in 4 for my numerator degrees of freedom and 115 for my denominator degrees of freedom. And I'll hit OK. And then the process of finding the p-value is pretty much exactly the same as we did for chi-square. So we're always going to choose right tail, and then you're going to put your test statistic down here in the bottom, which I think was 10.19, and then you click on OK. And then the floating box is the p-value. So for F distribution, always click right tail, enter in your test statistic in the bottom box, and then the floating box is your p-value. And remember that anytime it starts using scientific notation like this, then your p-value is essentially 0. Because what this means is that I would move that decimal place 7 places to the left, which gives me 0.0000043 for my p-value. So back here, that's where I find my p-value. I got this, which was essentially 0, so I'm just going to put 0.000 because if I rounded that to 3 decimals, that is what I would get. So my p-value is very, very close to 0. When p is low, HO must go. So our conclusion, we're going to reject the null hypothesis. And if you look back up at where we wrote the hypotheses, we're going to conclude that the alternative is true. So we're going to say we reject the null hypothesis. We have very strong evidence that the average length of cuckoo eggs is different for at least one species. So in other words, we're saying that at least one mean is different. All right, I'll give you a second to write that down. That's basically the fundamentals of doing analysis of variance. Next, we're going to do another example where I'm going to show you how to do everything, including putting the data into StatKey to get your results. And on the next example, I'm going to show you how to do the follow-up analysis that we talked about. So remember, our 2-step process here is do the overall test, which is what analysis of variance is in this case. And then the second part, if that overall test is significant, then we're going to do a detailed follow-up analysis. All right, so for this next example, you might want to have StatKey up on your computer too and do it along with me. That might help you remember better when you're doing your homework on your own later on. And this data that we're going to look at, we've actually looked at part of this data set before and compared just 2 of the groups before. But when this study was done, they actually did it where they compared 3 groups. So analysis of variance is the appropriate way to analyze this data. So this is about odors and time spent at the restaurant. So businesses know that customers often respond to background music. Do they also respond to odors? Nicolas Guin and his colleagues studied this question in a small pizza restaurant in France on Saturday evenings in May. On one evening, a relaxing lavender odor was spread through the restaurant. On another evening, a stimulating lemon odor, and a third evening served as a control with no odor. The 3 evenings were comparable in many ways, weather, customer count, and so on. So we're willing to regard the data as independent simple random samples from spring Saturday evenings at this restaurant. Is there a difference in the mean time spent in the restaurant for the different odors? So they had these 3 evenings. One day they did lemon, one day they did lavender, one day they did no odor, and they want to know if people stay in the restaurant longer, depending on the odor that is present in the restaurant. So first thing we're going to do is define our parameters and write the hypotheses. So mu1 would be the mean time spent in the restaurant with the lavender odor. Mu2 would be the mean time spent in the restaurant with the lemon odor. And mu3 would be the mean time spent in the restaurant with no odor. So our null hypothesis, remember it's always that all the means are equal. So we're going to say mu1 equals mu2 equals mu3. And then the alternative hypothesis is that at least one mean is different. So if you wanted to use the word mean here instead of putting a symbol for mu, that would be just fine also. And if you wanted to say that at least one mean is different from at least one other mean, that is also correct. All right, so we got our hypotheses going here. So the first thing that we always want to do is graph our data. And remember the type of data that we're collecting here, our response variable is quantitative, time spent in the restaurant. And our explanatory variable is categorical. It's the odor, right? So I have one categorical and one quantitative variable. So the types of graphs that are going to be appropriate for this kind of data are going to be these stacked or side-by-side box plots. We could look at stacked histograms, stacked dot plots, or any of those kind of things. Any graphs for one categorical and one quantitative variable. So here I've done box plots of the data, and just looking at my box plots, does it seem like there's a difference? Does it seem like at least one of the odors had a different mean time spent in the restaurant than the others? What do you think? Yeah, I see a couple yeses there, and I think so. I think it looks like people spent a little bit more time in the restaurant when the lavender odor was present. All right, so next we're going to check our conditions. So first condition is that all the populations are normal or all of our sample sizes are at least 30. So looking at my sample sizes over here, lavender is 30. So that one's good. Lemon is 28, so not sure about that one. We'll come back to that one. No odor is 30, so that one's good. So lemon is not 30. It's pretty close, but not quite there. So if I look down at lemon on my graph, though, does lemon look reasonably symmetric with no extreme outliers looking at this box plot? Yeah, it looks pretty good. So even though it didn't have a sample size of 30, because the data for lemon was reasonably symmetric with no outliers, then we would say that it meets this first condition. All right, next we're going to look at our second condition, that of equal variability. So the condition is that all populations have the same variance, and the way that we test that is with our rule of thumb here. So our rule of thumb is that the largest sample standard deviation is less than twice the smallest sample standard deviation. So if I look at the standard deviations for all my groups here, the largest one is lemon at 15.438. Okay, note that we're not going to look at the overall, we're only going to look at the 3 individual groups. And then my smallest one was lavender at 13.105. So if I take 2 times 13.105, I get 26.21. So my inequality becomes 14.38 less than 26.21. Okay, once I've done all the numbers, then I look and say, okay, well, is this a true statement? Is 15-ish less than 26-ish? Yes, it is true. So because it's a true statement, that means that we do satisfy this condition for equal variances. So overall then, yes, we meet the conditions because either our sample sizes were large or the data itself was normally distributed, and the largest sample standard deviation was less than twice the smallest sample standard deviation. All right, so now we've written our hypotheses, we've graphed it, we've checked our conditions. We're ready to go ahead and start looking at our test statistic, that F-test statistic. And associated with that F-test statistic are going to be the degrees of freedom. And since this is like the one thing I can ask you to compute for this part, then we're going to compute it. So we're going to look at the numerator degrees of freedom and the denominator degrees of freedom. So first of all, starting with our numerator degrees of freedom, remember numerator degrees of freedom is equal to k minus 1. So numerator or groups degrees of freedom equal to k minus 1. In this case, we had 3 groups that we're comparing. So 3 minus 1 is 2. So I have 2 numerator degrees of freedom. For my denominator degrees of freedom, we're going to have n minus k. So n is 88. We can see that. Here we go. Here's the overall number. So this is my n. And number of groups being compared was 3. So I'm going to have 88 minus 3, which is 85. So I have 85 denominator degrees of freedom. All right, so now I figured out how many degrees of freedom I have, and I'm actually ready to go ahead and start doing the analysis. So we're going to walk through how to do this analysis inside of StatKey. And this data, I've put it on Blackboard. So in Blackboard, you're going to find where it says course links. And then under course links, you're going to find cool data. And then you're going to download the odors 3 data set. So it's called odors3.csv. Okay, this is the data for this problem that we're working on. So if you're doing this along with me, which I recommend so that you remember how to do it when you get to the homework, then go to Blackboard, choose course links, scroll down to where it says cool data, and then you're going to download that odors3 CSV file. Once you've downloaded that file, then go back to StatKey or open up StatKey if you don't have it open already. In StatKey, where we're going to go here is at the bottom where it says ANOVA for difference in means. So in StatKey, you're on the very bottom row, third one over that says ANOVA for difference in means. This is how we're going to have StatKey compute that F statistic for us. So click on that. And then we're going to upload the file that you just downloaded. So you're going to click on Upload File, and you're going to find that odors file wherever yours is. Mine's in my Downloads folder, and click on Open. Okay, once you do that, so you've clicked on Upload, you found your odors file, then it just wants you to identify what's your categorical variable and what's your quantitative variable. And it's color-coded. You might remember this from when we've done this in the past. The quantitative variable it wants first, and it's going to color-code it kind of a teal, seafoam green color. So our quantitative variable was time. So I'm going to click on where it says time. And then my categorical variable was the scent, the odor. So I'm going to click on odor, and it's going to color code that yellow to go with my categorical. So once you've identified your quantitative and your categorical variable, you can click on OK. And just like with the chi-square, we're not going to be doing any randomization things with the ANOVA test. So you can ignore the big graph and all this stuff over here. You're not going to press generate anything. In fact, once you've uploaded the data, you're done. Like if you look over here under original sample, look at that. It gives you the F statistic just that easily. Pretty handy dandy. Okay, and it also gives you summary statistics for the original sample. So we've got the sample size, the mean, and the standard deviation for all 3 of the groups that we're comparing here. So when we're looking for the test statistic, this is it. Okay, it's this F equals 10.861. And if you want to see what the full analysis of variance table looks like, then right where it says original sample, right next to that, there's a little bubble or a little button that says ANOVA table. And if you click on that, then it's going to show our full, well, mostly full analysis of variance table. Okay, so you can see your F statistic is in there. You can even see the degrees of freedom. So in the analysis of variance table, it doesn't call it numerator and denominator anymore. Now it's calling it groups and error. But you can see the groups degrees of freedom was 2. That was our K minus 1. And the error degrees of freedom is 85. That was the 85 minus 3. So those are the two numbers that we got before. All right, everybody do okay figuring out how to make it do that F test for us? All right, good. So we have this test statistic, but unfortunately, StatKey doesn't just come right out and give us the p-value for it. I wish it did, but it doesn't. So we're going to have to go in and find the p-value ourselves, the same way we did with that Cuckoo bird data. Okay, so write down the test statistic that F equals 10.861. And then I'm going to come back to the main menu of StatKey, and this time I'm going to choose the theoretical F distribution. So in my main menu for StatKey, I'm choosing the theoretical F distribution. It's going to ask me for my degrees of freedom. So I had 2 numerator degrees of freedom and 85 denominator degrees of freedom. So I'm going to put those numbers in there. And then I'm going to click on OK. And once in here, just like before, I click on right tail. I enter in that 10.861. Is that what it was? I didn't write it down. I told you guys to write it down, and then I totally didn't follow my own advice. So if I'm doing the wrong number, somebody stop me. So I put in my test statistic, that 10.861, and then the floating box is my p-value. So my p-value is 0.000063. So we get the F statistic and we get the p-value in 2 different spots on StatKey, which is almost identical to what was happening when we did the chi-square distribution last time. So you should be a little bit familiar with that process. All right, so coming back here, this just shows where I got those numbers from. Looking at my hypotheses, my F statistic 10.861, my p-value 0.000063, that's really, 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 really low. And when p is low, HO must go. So we're going to reject the null hypothesis. We have sufficient, or you could even say super strong, because in this case, our p-value is really low. So we have really strong evidence that at least one mean is different. So at least one of the odors had a different mean time spent in the restaurant. All right, so now we've done this overall test. We found out that at least one mean is different. Now we want to go ahead and do our follow-up analysis so we can figure out which mean or means are different from each other. And what we're going to do for that follow-up analysis is we're going to create confidence intervals for each of the groups. So our follow-up analysis, we're going to look at confidence intervals for each group's mean. And our confidence interval, rather than being individually done for each group based on their own individual standard deviations, because we've already met that condition where we have equal variability, then we can actually have a better estimate for variation by using a pooled standard deviation. So that pooled standard deviation is called MSE, or the mean squared error. And I'm going to show you how to find that, and I'm going to show you how to use it in our confidence interval formula. So the formula that we're going to end up using is, and we're going to do this separately for each group, we're going to take x bar plus and minus t star times the square root of this MSE, which I'll show you where that is, divided by square root of the sample size. And this t star here is going to be based on the error degrees of freedom, the denominator degrees of freedom. So again, because we're kind of pooling everything together, it's going to give us a higher number of degrees of freedom to work with as well, which is going to give us a narrower confidence interval and all kinds of good stuff like that. So T star has degrees of freedom equal to the error or denominator degrees of freedom. So in other words, n minus k. And the MSE is what we call the mean square error. And it can be found in that analysis of variance table. And I'm going to show you where to find that. And then, so we're going to construct a confidence interval, one for each group. And remember, a confidence interval tells us this is where all the plausible values for that mean are. So when I do the lavender one, this says, hey, this is all the plausible values for the mean for lavender. When I do the lemon one, it says, these are all the plausible values for the mean for lemon. So I'm going to look at these confidence intervals, and if the confidence intervals overlap, meaning they have values in common with each other, then it would be plausible that those are the same. So we don't have evidence that they are different, right? But if our confidence intervals do not overlap, that means all the plausible values for one group are different from all the plausible values for the other group, then we're going to say that means we have evidence that they are different. So this is how we're going to decide which groups are different and which groups are not different from each other. So in StatKey, remember, if you click on that box for analysis of variance table, and I'll go back and show you that real quick in case you forgot already. So this is in the original ANOVA for difference in means when we were finding the F-statistic and putting my data back in there. Okay, so I have F equals 10.861 up here. If I click on that ANOVA table, the number that I'm looking for MSE, so I'm going to look at the MS column, and E stands for error. Okay, so I'm going to look in the row for error and the column for MS. And where those intersect, that is the MSE number that I want to use in my formula. So in this case, that is the 210.3. So you can see that here. So the MSE is 210.3. Now, next I need to also know my T star value. So the degrees of freedom for T star are the denominator / error degrees of freedom, which in this case was 85. So I find that T star just like I've been finding T stars all along. I would go in to the T theoretical distribution, and I would click on two-tail, and pretty much we're always going to use a 95% confidence interval for these. That's just kind of the standard that everybody uses. You could use another level if you wanted to, I guess, but in our class we're pretty much just always going to do 95. So unless it tells you something different, always do 95. So but 95 there, and then our T star value is going to be down here at the bottom, the 1.988. And remember that we're using that denominator degrees of freedom as our degrees of freedom to get our T star value. So once I've done all those things, then I'm ready to go ahead and start using my formula. So remember, I got that MSE from the ANOVA table. I got my T star using that error degrees of freedom. And so now I just need the mean and the sample size for each individual group. So I'm going to construct a confidence interval separately for each group. So I'm starting with lavender. And if you run into problems on your homework and you're looking for like clarification from the textbook, this part, the follow-up analysis, actually comes from section 8.2, not 8.1. Most of what we've talked about comes from 8.1, but this little part comes from 8.2. So keep that in mind if you're stuck and looking in the book and you're like, I don't know what she's talking about. This wasn't here. It's in 8.2. Okay, so for lavender, my sample mean was 105.7. So I'm going to have 105.7 plus and minus my T star, which is 1.988 times the square root of that MSE, so 210.03 divided by square root of the sample size for lavender, which was 30. So now I'm just going to work through those numbers there. So I'll do the square rooting numbers over here first. So I have the square root of 210.03 divided by the square root of 30. And really, mathematically, that's the same as just taking the square root of, you can do the division first and then do the square root of the whole thing if you want. Mathematically, it's the same. So I get 210.03 divided by 30. Then I'm going to take the square root of that number. Gives me 2.6459. Put that here. And then I'm going to multiply that by my T star, which is going to give me my margin of error. So I take that result, multiply it by 1.988, which gives me 5.26. So my margin of error here is 5.26. So now I'm just going to take 105.7 minus 5.26, which gives me 100.44. Then I'm going to take 105.7 plus 5.26, which gives me 110.96. And that's it. That's my confidence interval for lavender. And I interpret this confidence interval just like we've always been interpreting confidence intervals. So we would say we are 95% confident that the mean time spent in the restaurant with lavender odor present is between 100.44 minutes and 110.96 minutes. So that is 1 out of 3 confidence intervals that I need to do. So I've done it for lavender. Now I need to go do it for lemon and also for no odor. So I'm just going to keep chugging along over here. If you run into any problems or if you have any questions, feel free to jump on the chat window and let me know while we're going along here. Okay, so for lemon, my mean was 89.8. So I'm going to have 89.8 plus and minus my t-star, 1.988, times the square root of 210.03 divided by square root of 28. So the sample size for lemon was 28. So I'm going to get 89.8 plus and minus 1.988 times, so 210.03 divided by 28. Then I square root that number. So 2.7388. All right, so then I multiply that by 1.988. And now I've got my margin of error for this confidence interval. And that margin of error is 5.44. So now I take that 89.8 minus 5.44, which is 84.36. And then I'm going to take 89.8 plus 5.44, which gives me 95.24. All right, so there's my confidence interval for lemon. So I'm 95% confident that the mean time spent in the restaurant with lemon odor present is between 84.36 and 95.24. And finally, I'm at no odor. I'm going to do the same thing. So for no odor, the mean was 91.3 plus and minus 1.988. Times the square root of 210.03 divided by square root of 30. So I do that calculation. I end up with square root of 210.03 divided by square root of 30 is 2.6459. So I get a margin of error of 5.26. So margin of error for no odor and lavender is exactly the same. So is that just a happy accident or is that on purpose? Why do they have the same margin of error? Just got lucky, or is there a reason why they would have the same margin of error? What's the same about no odor and lavender that's different from lemon? The sample size, exactly. So if you have groups that have the same sample size, then they'll have the same margin of error. So that can be pretty helpful if you can recognize that in your homework or whatever problem you're working on. If you end up with groups that are the same size, then it can save you some calculation work because they'll have the same margin of error. So for no odor, I'm going to take 91.3 minus 5.26, which gives me 86.04. And then I'm going to have 91.3 plus 5.26, which is 96.56. All right, so we're 95% confident that the mean amount of time spent in the restaurant with no odor, just the regular pizza odor, is between 86.04 minutes and 96.56 minutes. So now I've got my 3 confidence intervals. Now I can start looking for overlap, no overlap, and be able to draw conclusions based on that. So here's my 3 intervals. All right, and let's look at lavender. Let's compare lavender and lemon. So do the lavender and lemon intervals, do they overlap? Do they have any values in common, in other words? Are there any values in the lemon interval that are also in the lavender interval? No, right? So there's no overlap. So that means that lavender is different from lemon, okay? And lavender had a higher mean than lemon based on their numbers. Okay, what about lavender and no odor? Does lavender have any of the same numbers in common with no odor? Nope, not again, they don't have anything the same, right? So that means that lavender is also different from no odor. Okay, so lavender is different from no odor, and lavender has longer time than no odor. Okay, what about lemon and no odor? Do they have any values in common between those two intervals? Yeah, they have a bunch of overlap, right? A bunch of values in common. So that would mean that we don't have any evidence that lemon and no odor are different from each other. So our conclusion then is that lavender is different and that people stay in the restaurant longer with lavender, but we don't have any evidence of a difference between lemon and no odor. And that's how we're going to use our intervals to draw conclusions. It's important that you use the intervals to draw your conclusions. Sometimes what I see on the test is people go to all this work, they compute all these intervals, and in the end, when they draw their conclusion, they'll tell me lavender had the most, no odor had the second most, lemon had the least. Well, that's not based on your intervals, right? Our intervals said that we don't have any significant difference between lemon and no odor. So it doesn't really matter that in our sample, no odor was higher than lemon. Our results say that the difference could have occurred due to chance. So we show no evidence of a difference between lemon and no odor. The only one that we show evidence of a difference of is lavender, and lavender is more than both lemon and no odor. So be careful how you word things in your conclusion, because if your conclusion sounds to me like you're saying lemon and no odor are different from each other, then I'm going to mark it wrong. So again, in this one, we're just saying lavender is different. It's more than the other two. Lemon and no odor show no significant difference from each other. All right, a couple other things I was going to show you guys. I was just going to show you some different, something besides StatKey, looking at the analysis in another program. So this is some software output from another program called Minitab that's pretty commonly used. StatKey is really fantastic for our class. It pretty much does exactly what we need it to for our class, but nothing else. So in the real world, like real analysts don't really use StatKey because it's not that powerful. So if you were actually to use statistics in your job or something like that, you would probably use another program such as Minitab, or SPSS is used a lot in the social sciences. Then if you get like really big data sets, there's several different programs out there that you might possibly run across. But basically in all these programs, when they do this analysis of variance, you're just looking for this analysis of variance table down here, making sure you can find that F-statistic and the p-value. And in like Minitab, it actually will go ahead and give you the confidence intervals already for you, which is pretty handy.